go ahead and record this. Okay, so we're working on our basic integration problem, and problem number 15. 15 goes integral of x to -1 power plus 2 squared dx. Let me change that so it can be a little better. Okay, now these types of problems, you could try doing u sub real quick, and then I'll go ahead and say, hey, what if u was this guy here? But do you really want to take the derivative of x to the -1 power? And if you do, that'll be rewritten as d over dx 1 over x right? Which looks so confusing. So instead that we can do power rule. So it'll be -1 x to the -2 power. How did I do that? Is because remember when you do power, you bring the exponent to the front, and we minus 1 to it. That's why it's a -1 in the front, and -1 minus 1 is -2. To rewrite this is -1 over x squared. Now, if I did do u sub, is there a x squared here anywhere that I can divide by? No. So u sub would have failed. And it's okay to try u sub, especially when something looks so complicated. And then if it doesn't work, it doesn't work. Let's try another way. And the other way of doing these integrals is to just expand the problem. So if I take the integral, and then if I expand the problem out, it's going to be x to -2 power plus 2 and 2 make 4, x to the -1 power plus 4 dx. Okay? Because this is x to -1 plus 2 and x -1 plus 2. And if I multiply these together, that becomes -2. And when I multiply 2 times x -1, that's 2x to -1. This guy would also give me the similar 2x to -1. That's how I got 4. So if you worked on your algebra 2, there's a fast way of scoring a binomial. And then 2 times 2 is 4. Now, for us to take the integral, we can take 3 separate integrals. Now, I'm writing it so you guys can see it. But in practice, don't separate them. Like, you save a lot more time when you don't have to rewrite the whole problem. So I'm going to rewrite this, though, as a positive exponent. You could, just to look at it, but we're not going to use it. This is really an integral of 1 over x squared dx. Sorry, -1 here. This is really the integral of 4 over x dx. And this is the integral of just 4, right? Just look at it. But us rewriting it actually doesn't help. Only one that does help is maybe the middle one. So I'll leave him out. But the integral here is just power rule. The first one is just power rule. N plus 1 over n plus 1, which is n being the exponent that I already have. So we're left with x to -1 over -1, okay, and plus c. And then we're going to write a common plus c for everyone. So this is going to be x to -1 over -1. This guy here in the middle, you can rewrite this as instead 4 integral 1 over x dx. And that's an identity that we know. That's natural log. So it'll be plus 4 natural log absolute value of x. And the last part, the 4 integral of 4 is just plus 4x. I can rewrite some of this stuff as 1 over -1 over x plus 4 natural log absolute value of x plus 4x, and then don't forget the plus c at the end. Let's check on the left. Yep, that's our answer. They left it actually at this one right here. Okay, this is problem number 10 on homework 3. And it goes integral of 4 sine x cosine of x dx And when we're looking at this problem, first thing we should try is that an identity that I know? Nope, no, there's no identity for me to know sine, cosine. So we're gonna pick a U substitution. So you can pick a sacrifice. You can pick either sine or cosine as your sacrifice. I'm gonna choose sine because the derivative of sine is cosine. But if I took the derivative of cosine, I would end up with a negative. I don't really want that negative, just in case I make dumb mistakes. So if U is equal to sine of x, and derivative of sine, du is cosine of x dx. Dx is equal to du over cosine of x. So make sure you just write your work, and you get in a pattern of doing it pretty quickly, and not messing around some dumb stuff. I'm gonna take 4 out because that's a constant. Sine we rewrote as, see now that is just the letter u, and then cosine of x, and x became du over cosine of x. That nicely divides out to 4 integral of u du. The integral of u, that's actually just going to be power rule. So 1 plus 1 over 1 plus 1. That's our integral. 4 u to the squared over 2 plus c. 4 cosine squared x over 2 plus c simplifies, become 2 sine squared x plus c. Whoa, what the hell did they write? No, I wouldn't have taken that. Yeah, that's probably answer for something else. Yep. Hi, folks. We made some adjustments. If you guys are tuning in to YouTube, that we had stopped previously right here, and we thought that was the right answer. And that is not a wrong answer. It's just that the answer that they gave us for number 10 was a little off. And the reason why is because they used the power reducing formula. And once they multiply the 2 from the power reducing, they called the constant 1 plus c to just be another constant. If you had approached the problem from a cosine as your U substitution, you should end up with something like this, which is not wrong. But once I do a power reducing, we end up simplifying to get this. So go ahead and pause the video and just look through these problems, okay? Okay, today's lesson will be on this inverse trig function. And I was told that Miss Yagi had covered the derivatives on the left side. So every time we do a derivative, we have to do the integral to go backwards. And these are the idea of inverse, undoing the problem. Now, let me see if I can mark this up. Can I just run it? No. Edit. Nope. Okay, well, let me screenshot it then. Run another screenshot. Okay, so the idea of the derivative inverse, it gives this funny square root. Take the derivative 10 inverse, it gives you this funny without a square root. And secant gives you a opposite value in front. Now, hopefully you guys memorize some of these patterns. For instance, tangent is totally off, so that's why there's no square root here. And for sine, it's just 1 minus u squared. And this u prime is our chain rule. So, a quick example of this. Get rid of that. When you guys had a problem that said the d over dx, darn it, of sine inverse of, let's say, 2x. The way we took it is we just copied the identity. It's 1 over the square root of 1 minus 2x squared, right? We're straight copying times u prime, which is the chain rule, the derivative of 2x, which is just 2. So this answer would be 2 over the square root of 1 minus 4x squared. I gave you the derivative d over dx, tangent inverse of 2x. Same thing, it's just straight copy. 1 over 1 plus 2x squared times the derivative of the inside, which is just 2. And if I do d over dx secant inverse of 2x, it's just a copy. 1 over absolute value of u, which is just copying the 2x, square root of u squared, which is just copying the 2x, minus 1. Chain rule, multiply by 2. But if we want to go backwards, like, it has to fit this format. And the formats that we're looking at are specifically these here. If it doesn't fit the format, we can't use it. Sorry. So let's give ourselves an example to start off with. I give you guys give me 1 second. The integral of 1 over square root of 4 minus x squared dx. First thing, when I see this problem, I see a square on the bottom. I'm like, what the hell am I supposed to do? I would try u substitution. And if I said u was equal to 4 minus x squared, du would be negative 2x. And I don't have a negative 2x here to get rid of. So we can't use u sub. If this problem was written as integral of 2x over square root of 4 minus x squared, yeah, this is just a u sub problem, because the 2x would have divided out. But as you can see in our problem as we start, we don't have that. So you'll realize that it's not a u substitution problem, because if you try to pick a u substitute, you end up having no one to divide by, having leftovers still. So this identity, does it look like a sine, arctangent, arcsine, or arcsecant? Couple hints that the x, the order kind of helps you. If I have the constant first, that's going to be arcsine. If I have the variable first, that's going to be arcsecant. If I don't have any square roots at all, that's going to be arctangent. So again, if the constant is first, it's sine. If the variable is first, it's secant. And one thing I like to look at is that if you look at arcsecant, integral of du over u squared root of u squared minus a squared, where u is my variable, they're next to each other. And for some reason, I think it's like you visiting someone in prison. See how you're next to each other? So the u substitute has to visit the u substitute, but they're not really a substitute. Okay, so u and u. Isn't u prime example 2? Oh, u prime. Pause. Okay, so we are figuring out which one are we going to use for this problem: sine, arctangent, or arcsecant. So because we have a constant first, what we're going to use is sine. So you just have to make sure you have the variables correct. As you see in the identity, it goes sine first. I'm sorry. it goes a squared. Now what value would be, not a squared, what value would be a? So we just have to write a is equal to 2, because 2 squared is 4. And our u value is going to be x, because u squared is x squared. Okay? So let me erase this part up here. So this becomes straight copy arc sine of u, which is x, over 2 plus c. Or another way of writing arc sine is sine inverse of x over 2 plus c. It's a straight identity. You make sure you copy your u and the a. What if the problem changes? If I write an integral of 1 over the square root of 9 minus x squared, is that sine, tangent, or secant? Arc sine, arc tan, arc secant. Well, constant first is going to be sine, so it's sine inverse. A is 3, u is x. That's straight identity, so it's x over 3 plus c. Okay. But what if my u value was not so nice? What if I wrote instead the integral of 1 over the square root of, let's say, 9 minus 4x squared? So dx, I've got the dx here. We do something very similar. We say a is 3, and then u is 2x. But the problem is, as we rewrite it, our goal is actually, what we're doing is we're saying, hey, we're rewriting it. If 9 is really 3 squared, which is really a squared, and u is 2x, that becomes minus u squared. Does that work for us? And that's where this problem ends up having u substitution. Whenever the u value is not a clean x, you need u substitution. So we're going to say that it's integral of 1 over square root of a squared minus u squared. And what happens to dx? Well, how do we get dx? We just take the derivative of u. So dx becomes du over 2, just like in u substitution. We rewrite it. 1/2 goes out. Du over square root of a squared minus u squared. That looks just like my identity. 1/2 sine inverse of u over a. U is 2x and a is 3. Let's do a different problem. We'll see kind of the pattern. We're at the integral of dx over, let's say, 9 minus x squared. No square root. Sorry, the plus. Does that look like sine, tangent, or secant? No square root. You could try u substitution. Hey, if u was 9 plus x squared, du would be 2x dx. Is there 2x I can divide out? Not u sub. So we have to rewrite it, saying, hey, u substitution is not going to work for this. Does this match one of my inverse trig identities? Because I have a fraction. And because there's no square root, it does match my tangent one. So let's go ahead and rewrite the variables to make sure we have all our parts. If a was 3 and u was x, this could be replaced with the integral of 1 over 3 squared, which is a squared. Our x became u squared. And just to say this, the derivative of u is dx. So every time I see dx, I can write du instead. That's my straight identity. 1 over a arc tan. Let's write it the other way. Let's use tan inverse. inverse of u over a plus c. Plugging in our a's, our u's, and our a's, 1 over 3, tan inverse of x over 3 plus c. What about if this was for arcsecant? The integral of dx over 3, no, sorry, x square root of x squared minus 9. Now, if you look at this problem, this really doesn't look like sine. It really doesn't look like tangent. And one of the hints is if you see the variables next to each other on the outside, or maybe you have to rewrite it to force them that way. This is going to be u is x and a is 3. 1 over, well, let's rewrite it. This is integral of du over u squared of u squared minus a squared, which is 1 over a secant inverse of u over a plus c. And we're really just plugging in all our variables. So if I want to plug it back into this version, a we said was 3, secant inverse. U we said was x. A we said was 3 plus c. So you have to get used to seeing these problems and identifying which one is your u and which one is your a. So if I give you a question, which one would I use? The integral of 1 over 16 minus x squared dx. Does that look like a sine, tangent, or secant? Why is it 3? Back here, the reason why is because it's always u squared minus a squared. So a squared is 9. So a has to be 3. It's always the square root because we're always squaring our u and our a values. So if my value is 9, a had to be 3 because 3 squared is 9. Okay. Let's take this other example, which is not going to be 3. So is this sine, tangent, or secant? I don't see a square root. You could try u substitution. That's going to be negative 2x. I don't have a negative 2x up here to worry about. Nope, not u sub. I tried it. I wish it was. So in this match, no square root is a tangent. So this is going to be a is 4 because 4 times 4 is 16. And then u is x because x times x, x squared. I didn't make a mistake. Let me change to the plus. I'm sorry. Make that to a plus. It doesn't work if it's a minus because it's not the right identity. And then we end up with equals 1 over 4, 10, inverse of u over a plus c. Now, just let's double check it. If I look over here on my left, if I took the derivative of this, what if we say what's d over dx of 1 over 4, 10 inverse of x over 4? Would we end up with our answer back here? Well, let's try. It's a little messy, but okay. 1 over 4 stays the same. And the derivative of tan inverse, we said, was 1 over 1 plus u squared, where u is going to be x over 4. After we take the derivative of tan inverse, we have to do chain rule. We multiply this by the derivative of u, which was x over 4, which gives us 1/4. Now we see 1/4 on the outside and 1/4 inside. Let's go ahead and multiply those together. Multiply these together. That will be equal to 1 over 16. Now I'm going to do a couple of fancy things. 1 plus, let's go ahead and square that. That's x squared over 6 15. Common denominator would be 16. 1 over 16. 1 over 16 over 16 plus x squared over 16. We can factor out 16. 1 over 16. 1 over 16 plus x squared. 1 over 16. Do you guys like dividing fractions? We say multiply by the reciprocal. 1 over 16 times 16 on top, because the reciprocal would give you 16 over 1. 16, I don't need that parentheses anymore. 16 plus x squared. We simplify the 16 over 16. It's 1 over 16 plus x squared, which is our crazy answer. Back over here. Just to prove that this would have worked. Okay, let me pause. So this next problem is going to be a little crazy looking. It's going to be the integral of 20x to the 4th over 4x to the 5th square root of 16x to the 10th minus 4 dx. Does this look more like a sine problem, a secant problem, or a tangent problem? Well, no, that means there's a square root, so it can't be tangent. I see a variable first instead of the square root. That's most likely going to be secant then. And we have our little friend visiting us. Hey, friend. Is 4x to the 5th squared 16 to the 10th power? Yeah, it is. So we know this is a secant. So let's go and set up the secant problem. If I say u is equal to 4x to the 5th, and then I say a is equal to not 4, remember this is a squared, this is going to be 2. Now let's rewrite this problem as much as I can using our new variables u and a. This is the integral of 20x to the 4th of u, because remember that's a u now, square root of, that's the u squared, and that's an a squared. Now, if you look at our left side, that kind of looks like it. Now, we're still in dx. It doesn't matter if you square root, if the root number isn't squared. If it isn't squared, then you have to, your a value would be, for instance, square root of 2. Let's say if a squared was 2, then a would have to just be a square root. And you just write it as a square root. So here's our problem. I have an x and x. How do we end up swapping dx for a u? Take the derivative. Du is equal to 20x to the 4th. Guess what? We needed that. Let's rewrite it. Dx is equal to du over 20x to the 4th. We're going to plug that in. Integral of 20x to the 4th over u square root of u squared minus a squared. And dx is now written as du over 20x to the 4th. We're going to copy it from this guy here. And lucky for us, simplifies out. And we end up with exactly the identity that we were hoping for. Du over u squared of u squared minus a squared. No leftover constants, no leftover x's. And this is a straight identity from our secant identity. Equals to 1 over a. What's a? A was the number 4, I think, right? Oh, 2. Row 2. What's up here? What's up here? Oh, sorry. Darn it. I miscopied it. Oh, no, that's right. And then we write secant inverse of u over a? Well, u, we said, was 4x to the fifth. A we said was 2, and then plus c. It's a straight copy. Okay. Hopefully that was helpful. I'm going to give you guys a worksheet today with about 8 questions for you guys to practice this. Maybe I'll make it 10, so it won't take you that much time. The answers will be included, so you guys can double check your answers. So if any questions, let me know. And I'll post this within the hour because I have another class I have to teach right now.